Welcome to Pavonars, webinars for the pavement community. Today we'll be talking about quantifying the effects of laboratory curing conditions on workability, compactability, and cohesion gain of cold-in-place recycling. This work is based on Dr. Sadie Casillas', previously Dr. Sadie Smith's, dissertation research that goes by the same title. Dr. Casillas received her Bachelor of Science from the University of Arkansas in Civil Engineering with honors in 2013, and she obtained her Master's and Doctor of Philosophy in Civil Engineering in 2015 and 2020, both from the University of Arkansas. And you can find out more about her LinkedIn profile, which is provided here. So first of all, what is cold-in-place recycling, or CIR? Let's pretend that you have a distressed hot mix asphalt layer on top of an old base, which is on top of subgrade. What cold-in-place recycling does is it mills 3 to 6 inches of that distressed bound material, so only the hot mix asphalt, and it injects water and stabilizing agents. And the stabilizing agent can be asphalt emulsion, asphalt foam, or other additives, and then you compact that milled material. You can place a surface on top, either a HMA overlay or a maintenance treatment, and then you have a new riding surface with a semi-bound material, which is a CIR, on top of the old base which rests on the subgrade. Now the current CIR mix design revolves around mixture components, which includes the reclaimed asphalt pavement or RAP, and ensuring that the RAP is coated by whatever additive you are adding. And you can find out more about this with asphalt emulsion in AASHTO PP86. However, then the second AASHTO standard provided looks at the final strength and stability, which is the performance of the fully cured mixture. And this can be found in AASHTO MP31. But as you can see here, Dr. Casillas anticipated some intermediate stages, and she looked at 3 different intermediate stages between what we currently have, identifying the mixture components and ratios, and looking at the final strength and stability. And these intermediate stages were workability, compactability, and cohesion gain. And the workability looks at mixing and placing the CIR. The compactability looks at densifying the CIR. And then there's the cohesion gain, which is when the asphalt emulsion is still containing water, and that needs to evaporate. And that evaluates the curing of the asphalt emulsion. So the breaking of the asphalt emulsion stage. Now, when we think about in the field, we have CIR trains, and this is the workability stage where you mill the material, you mix it, and it goes through the paver. But once it goes through the paver, you then start compacting it, and this is the compactability stage. And you can see 2 common rollers or a steel wheel roller on the left, and then a pneumatic tire roller, which you can see on the right. Now finally, the cohesion gain, this is when the asphalt emulsion component is curing in the field. And you can see here 2 different images of roads in various stages of curing. And those little wet spots in the right picture, that's where water is still coming to the surface and leaving it. And on the left side there, that's a pretty much fully cured road. And the CIR is in the lane that we're standing in. And then the lane next to it, that lane has not been treated yet. So that's the original pavement structure. So what Dr. Casillas looked at was looking at, let's take the mixture components and then evaluate their workability, compactability, cohesion gain, and then finally finish up with the final strength and stability. And we broke this down into the loose CIR material being workable and compactable, and then the compacted CIR leads to the cohesion gain. So we divided our work up into having loose CIR mixtures and compacted CIR mixtures. So starting out with the loose mixture, we have our pre-compaction curing. So after you mix the reclaimed asphalt pavement, the asphalt emulsion, and any sort of additives, you can let the CIR cure for 30, 60, or 120 minutes. And we had it cure at 10, 23, 40, and 60 degrees Celsius. We then looked at the workability and the compactability of the mix throughout these different stages. And in order to do that, we ran the loose triaxial test, which is kind of the gold standard of workability. We ran the Dongre workability test, which is kind of between workability and compactability. And then we leveraged some superpave gyratory compactive metrics in order to look at the compactability of the mixture. Then after we compacted the sample, we had curing regimes on the compacted specimens, and this was at 4, 12, 24, and 720 hours, and again at temperatures of 10, 23, 40, and 60 degrees Celsius, and this was all measuring the cohesion gain. And in order to quantify the post-compaction curing, or the cohesion gain, we looked at the Raveling test, the compacted triaxial test, and the direct shear test. So when we're looking at the workability using the loose triaxial test, we felt that the shear strength at 0 kilonewtons, which was 0 confining pressure, mainly came from the aggregate structure. We did have a membrane around the samples, but the majority of any sort of strength came from simply the aggregate structure holding some loads. But then once you get into the 100 and 200 kilonewton confining pressure, you see that the shear strength increases as the confining pressure increases. And this was expected in the loose triaxial test. We also found at 100 kilonewtons confining pressure, the temperature was statistically significant. Now, something we started noticing, and this will be a common theme, is that we found that 60 degrees Celsius might be too high of a curing temperature, or at least too high of a temperature to test the samples at, because we tested the samples immediately after they were cured. Therefore, they were at the temperature of the curing temperature, and we felt like at 60 degrees Celsius, we may have been activating some of the asphalt binder on the wrap. Therefore, the asphalt binder on the wrap was a little softer, and that may have impacted some of our results. But moving on to the Dongre workability test, which is a combination of workability and compactability, the trends were not quite as significant, and the DWT simply takes the stress difference at 650 kilopascals versus 550 and divides that by the corresponding strains at those stress levels. And we felt that the trends may not have been as clear or significant because the DWT was developed for trying to differentiate between hot mix asphalt and warm mix asphalt. So this is an asphalt concrete test, and these specific parameters shown in the equation on the right were what captured the difference between hot mix asphalt and warm mix asphalt. Therefore, cold in place recycling may not have been optimized to show any differences in this range. One reason potentially is because the densities are much lower, but there are many other possible reasons. And we really felt that although we analyzed all of the data using the official DWT analysis technique, we do feel like a deeper analysis is necessary in order to better understand the workability and compactability of CIR. Now looking at the compaction metrics, we found that the gyratory compaction might be more sensitive to lubrication than simply axial pressure, so having that kneading influence may have a higher level of sensitivity to the lubrication with the water and the asphalt emulsion in the mixture. We found for workability, we looked at WEI-CIR and N76 for compactability. We looked at the normalized shear index or NSI. And we found that the WEI, the workability energy index for CIR, had the best correlation to loose triaxial. Now there's a whole world behind these compaction metrics, and actually a previous student, Erica Young, she developed compaction metrics for cold in place recycled mixtures. So I encourage you to take a look at the May 23rd Pavinar, recorded in 2021, with that title, and you can learn all about these SGC compaction metrics for CIR. Now, when looking at the cohesion gain, we'll start with the Raveling test. We followed ASTM D7196, and we found the trend that the mass loss decreased as the cure time increased and the temperature increased, and this is expected. And all samples we tested passed the 7% mass loss, which is required in AASHTO MP31. But we do want to call out that the stiffness in the mix at 60 degrees Celsius may have dominated results. So if you take a look at the paper, you do see some odd things happening at 60 degrees Celsius. But if we were, in fact, reactivating the asphalt binder on the wrap, then that would loosen the top of that mix and you can have a higher mass loss simply because the mix was more tender, completely independent of any sort of cohesion gain of the asphalt emulsion CIR sample. Now looking at the cohesion gain for compacted triaxial, we found that there is low sensitivity to confining pressure, especially at the 4-hour cure. And this makes sense because these are fully compacted samples. We're not really expecting to see a whole lot of impact from the confining pressure. Now we did find that the shear stress increased as the cure time increased, and you can see that demonstrated here in this image as the stress increased, the cure time, or as the cure time increased, the stress increased, and the graph that's shown here is just the 4-hour cure. But we did find also, if you look at those 60 degrees Celsius measurements, especially for the cure time, some of those 60 degrees Celsius may have dominated the results. So we do need to be careful when looking at the 60 degrees Celsius. And finally, the cohesion gain with the direct shear. We found similar trends to both the Raveling and the compacted triaxial test. We did find that the cure temperatures were significant, the cure times were not significant, and we did find that significant curing may occur after 24 hours. And we found that there is a strong visual agreement between the compacted triaxial results and the direct shear. So we really find that the direct shear test, which is much easier to run than the compacted triaxial test, does have some potential merit, and it's certainly worth looking into in order to quantify the cohesion gain of CIR mixtures. So in conclusion, we looked at the workability, compactability, and cohesion gain of cold in place recycled mixtures. We found that in general, the curing temperature was more significant than the curing time. In order to quantify workability, we recommend the WEI-CIR as the best method. In order to quantify compactability, we found that the superpave gyratory compaction metrics were the best way to go. And then in order to quantify cohesion gain, we really feel that there's a lot of promise with the direct shear test. However, throughout this study, we established that experimental matrix that we saw earlier, and we found out that there were a lot of things during the sample preparation that we probably should have spent a little more time on. So we feel that when you're actually preparing the sample for CIR mixtures, there's a lot of things that need more exploration and evaluation in order to better understand what's going on when you're prepping those samples. So this is just a brief overview. If you're interested in learning more, I encourage you to take a look at the full paper. The link for the DOI can be found below, and you can download that paper and find more. But I hope you enjoyed this information, and I appreciate it and hope you have a wonderful day.